Hi, we're the blue team and we're presenting our research project on the mechanical difference between additive manufacturing produced and traditionally machined dog bones in static tensile testing. And my name is Dennis. We have
I'm Daniel.
I'm Sam. And I'm Dave.
and we will start. And so the objective of this was to test, analyze, and quantify the difference between AM produced parts and DMLS. We started searching and trying to figure out, okay, which material can we use, and we ended up on 17.4 pH stainless because that was what material we had access to. Our hypothesis was to use additive manufacturing, that the additive manufacturing samples were going to yield significantly lower mechanical properties such as ultimate yield strength, and elastic modulus than the machine samples. We thought this because the AM produced samples were produced with 100% used powder, which will contribute to lower mechanical properties, and we also didn't post-process the AM samples with HIP, which is hot isostatic pressing, which is generally used to increase the strength of AM samples. And so we followed an AFCM standard for printing and machining our dog bones. And so there's a set length and width, etc., that is specified by the standard that we used. And on the bottom picture, we see the printed part, and the black and gray is the speckle pattern that we used for our tensile testing, which we'll go over more later. And for our method, so we use 6 DMLS produced samples, and as well as 6 traditionally machined samples. The DMLS produced samples were sponsored by 3D Systems, and which we use 100% used powder, and which was sifted to 75 microns with a layer height of 30 microns. And then for the traditionally machined, we use the CNC to machine the additive part to machine the other dog bones. And then finally, after performing tensile testing, we performed SCM on both the samples in order to compare images. And so for the DMLS produced parts, that was supposed to be, we had produced them all in the same orientation because of the limitations of the machine, and also because we did not want to take up too much of the 3D System time that they were sponsoring us.
So, as Dennis mentioned earlier, we were following an ASTM standard for determining the dimensions of our dog bone samples. Just due to some difficulties with the production processes, we didn't exactly 100% hit the targets, but you can see here in this table we summarize what the exact dimensions were of each of our samples that we looked at during this study. So going real quick into the tensile testing setup, we used an MTS model 370.10 floor standing load frame rated up to 100 kilonewtons. And Dennis touched on this earlier, but to get strain data, we used a digital image correlation measurement system, which consisted of a camera that you can see here, the Basler ACE AC A645 100 GM camera, which is capable of delivering VGA resolution at up to 100 frames per second. And then we used the VIC 2D6 image processing software in conjunction with that. So here are just some example images that we fed into the DIC. You can see the speckle pattern there that Dennis touched on earlier. So these were the results that we got out of our stress and strain data. We unfortunately were not able to get data for the third machine sample and the first printed sample. The third machine sample, we had a camera malfunction, so we didn't have any images for the DIC to process. For the first printed sample, the BIC 2D6 processing software was unable to process all of the images, so we didn't get enough data to get the mechanical properties out of it. But other than that, for the rest of the samples, we have summarized here the elastic modulus, yield strength, ultimate strength, and ductility, as well as the averages for the samples. On average, the machine samples had a higher elastic modulus, yield strength, and ultimate strength, but a lower ductility. Especially when you look at the ultimate strength, you can see that there's quite a big difference where the machine samples on average had an ultimate strength of 1,313 megapascals in comparison to the printed samples, which on average had an ultimate strength of 648 megapascals. And here we just have some example stress strain curves. On the left is an example curve for the machine sample, and on the right is an example curve for the direct metal laser centered samples. And then the blue and green lines that you see are a remnant of the 0.2% offset method that we use to get the yield strength. We conducted paired t-tests comparing these four mechanical properties that you see here between the machine samples and the printed samples. They returned these p-values, which are all below the type 1 error rate that we set of 0.05. As such, all of the results are significant, meaning that there is indeed a difference between the two types of samples. And now I'll pass it off to Gabe.
The next step after the samples were tensile tested was to look at the fracture surface in the scanning electron microscope. So in order to do this, the fracture surfaces were not disturbed in order to try and maintain all the information on the fracture surface, and then the fracture surface was cut off about 5 millimeters from fracture surface. And then they were placed on a small metal pad and adhered with some carbon tape so that it could be conductive, and then it was placed in the scanning electron microscope. And this allowed us to gain resolutions of the surface from anywhere from 25x up to 10 to 20,000x, so that we could determine kind of what the internal microstructure looked like on when it fractured, as well as kind of determine where the fracture may have originated, as well as what type of fracture, if it was ductile or brittle. And so the first images here, the one on the left is of the printed sample, and the one on the right is of the machine sample. The one on the right, you can see a very definite shear band, and then you can see a lot of the radial lines that propagate out, which is very characteristic of a ductile fracture. And on the left, there's not much of a shear band, and it's not very characteristic of what a ductile fracture looks like, but it also isn't very characteristic of what a brittle fracture looks like either. It's pretty jagged and sort of uneven and different than what most materials are characterized as.
So, as Gabe was talking about, you can see on the additive manufactured sample, which is on the right, that we don't have a very distinct shear band. On the left, you see a very distinct shear lip on the machine sample right at the bottom of the image. Whereas on the right, it looks very muddled and you can't really tell what exactly is happening. You're also already beginning to see evidence of severe porosity in the additive manufactured sample. And as Gabe was talking about, the shear fracture begins at the center of the object, at the center of the specimen cross-section. Both of these images belong to the machine sample. In the one on the left, we see a very uniform shear plane where it starts right at the center. The image on the right shows the propagation. Here we have images of inclusions and precipitates for the additive manufactured sample. On the left image, we see spherical precipitates, or oxides. And these sit in very smooth-walled cavities, which indicate brittle fracture. On the right, we see inclusions, which are actually causing rastering in the image because it's non-conductive. So it gets saturated with all the electrons being shot at it and won't let any more pass through it.
So in both types of samples, we observed cuboidal-shaped precipitates to a much greater extent in the machine samples compared to the additively manufactured samples. In both cases, however, we did observe these cuboidal precipitates, and based on the very distinct morphology and the fact that other studies have found that 17.4 pH stainless steel, which is the material that we were looking at, when treated at the H900 specification, form BCC copper precipitates. So we believe that based on this distinct morphology and our experimental protocol, that these are indeed those BCC copper precipitates.
Here we see one of the propagation cracks up close, and this is on the machine sample, and we can see in the image on the right at the 5,000 times zoom that all of our cavities are cupped. We don't see any evidence of brittle fracture. Here is the additive manufactured sample, where we do see brittle fracture. In the image on the right, we see some step downs and what looks like cleavage where the two different boundaries meet each other. And when you have these smooth-walled cavitations or cavities in the object or the specimen, as you stretch it, the planes start to shift relative to the direction of the stress and induces brittle fracture.
To summarize our results and tie everything back to our hypotheses, we did see that the additive manufactured produced parts yielded lower mechanical properties in comparison to the traditionally machined parts. And we also found that the SEM validated that there are inconsistencies and issues with the printed parts, such as lots of voids, whereas the machine parts were really textbook fracture patterns.
So for future improvements, we would like to address the use of hot isostatic pressing for our additive manufacturing samples. This would yield an increase in the mechanical properties, whereas in our test we show a much lower mechanical properties for the AM samples than we did for the machine samples. It would also be interesting to look at different orientations for the print and see how that affects the non-isometric properties of the AM samples and test them in Tensile. And then lastly, we had mentioned that we used 100% used powder for our build. It would be interesting to vary the amount of powder that was used to produce the samples and how much that affects the mechanical properties. And finally, we would like to give a thank you to a number of people that had helped us out with this project.
Kevin Hines is a friend in Boulder who CNC machined the 17.4 stainless for us.
And Tyler, who was in the class for Tech 3D Systems, he helped us create the samples for additive manufacturing. Ruby took a lot of hours of his time off right before his thesis was due in order to help us out with tensile testing of all of our samples. And then Ty helped us look at the SEM and use the SEM and then compile images, as well as gave us a very educated hypotheses on what we were seeing inside our sample. And finally, thank you to Craig Bryce for this opportunity to do this project. And here are our references, and that concludes our presentation.